Welcome to Ready to Derive. In this video, we're going to learn how to calculate a definite integral. And what does that definite integral, how does it help us? What does it represent? It represents the area under the curve f of x from a to b. And this should look familiar. That definite integral is defined to be the limit as n goes to infinity of that summation expression, which is a Riemann sum. If this notation does not look familiar to you, you might want to watch my video, my previous video on Riemann sums and the definite integral, which I will link in the description below. So without further ado, let's begin. So let's review the definite integral definition, and we'll explain a little bit about delta x and xi star and f of xi star, just to review. So recall that this quantity here, this f of x of I star times delta x, is really just the area of one of those rectangles, and we sum them all up to find the total area, and then we send the number of rectangles to infinity, and that's how we get the actual area. So delta x is very important. Delta x is the width of one of these rectangles. So delta x, which is b minus a over n, is the width of these. We are assuming we are going to make evenly width rectangles. So I want to get into a little bit of review of x0, what xi represents before we get to xi star. So x0 is a and xn is b, and then we partition it up evenly by adding delta x every time. So x0 is just a, and x1 will be a plus the width of that rectangle is delta x. So logically, x2 will be a plus 2 delta x's. Sorry, that's a delta. xi will be a plus I delta x. And xn is just b. So where does that leave us? What exactly is xi? Well, let's call this the first rectangle, the second. This is the nth. Let's call this the ith rectangle. That means that the left endpoint of that rectangle, so for the first rectangle, the left endpoint is x0, for the second it's x1, so this will be xi minus 1. This right one will be xi. And xi star is just a sample point in that interval, xi star. It could be the left endpoint, it could be the right midpoint, or some randomly sampled point. So once we find x of I star, and we plug that into the function, then we get the height of the rectangle. So that will be f of xi star, right? So this is the height. And we know that the width is delta x, the width. And so that product gives us the area of a particular rectangle. Now, what we have to do is kind of decide what xi star is going to be. So more often than not, we'll be using xi star as the right endpoint. And why? Because if it's the right endpoint, xi star would be then, in this case, hold on a minute, xi star would just be x of I, which so it'll just be x of I, which we see over here is just a plus I delta x. And you'll see that that actually is the most simplest to use, because if we want to use the left endpoint, then we're going to have to use xi of minus 1. So let me just get that, sorry, xi minus 1. And what's xi minus 1? Well, it's not shown, but it's going to be the one before, so it's going to be I minus 1 delta x's. So a plus I minus 1 delta x. And the midpoint, well, I'm not going to really write that out in full, but you would just add those, the left and right, and divide by 2. But really, we are going to be focusing on using the right endpoints, because that's the simplest expression to use. And you can see why if we, and you see that it actually doesn't really matter that much, because if you take one of these rectangles, that's x minus I minus 1, that's xi, and the midpoint is in the middle of those two. As we increase the number of rectangles, they are going to get narrower, narrower, and narrower, to the point where the rectangle occurs at one point. And then the left, right, and midpoint, they're all one point, whatever x is there. And the height of this will be f of x. And the width, it's so narrow, we haven't even got a width, so we represent it with dx. And you see with that how that corresponds. So f of x is up here, it's the height of a rectangle with infinitely small width, dx. And of course, if we added up all those values, infinitely many times, and of course we get the true area under the curve. So before we get into evaluating definite integrals using Riemann sums, we need to review some summation formulas and results from pre-calculus. So if we have the sum of I as I changes from 1 to n, what exactly is that? That means, so I has to be 1, then it has to cycle through all the integers, 2 positive integers, plus 3, plus, all the way up to n. Then n times n plus 1 over 2 will give the sum of those numbers. And sum of I squared would be 1 squared plus 2 squared plus 3 squared, all the way up to n squared. And this is very cumbersome. We don't use this as much, but just for demonstration purposes, this would be 1 cubed plus 2 cubed plus 3 cubed, all the way up to n cubed. And a couple of other results. So if you have the sum of, say, a constant, c, from I equals 1 to n, that's a little, you feel like you don't really, there's nothing to add up because there's no i's in the body of the summation sign. But you have to realize that what that's really saying is take c and add it up n times. So c plus c plus c, that's 3 times, n times. So the result, if you're taking c and adding up n times, is just going to be n times c. All right, another result. What if we have c times ai? So now we do have I available or involved. So this would be ca1 plus ca2 plus ... I'll skip the third term right now, can. We can actually factor out the c's, and we would have a1 plus a2 plus ... plus an. So that tells us that we can, in effect, factor out a constant that doesn't have an I involved in it. So that would be true. And then the last result is kind of a common sense. We've seen this before with limits and things like that, is that if you want the sum of the sum of two terms, ai and bi, or the difference, you can just kind of, in a sense, distribute it and write it as plus or minus the sum of the bi's from I equals 1 to n. So you might want to make a note of these results, as we will be using them in the next practice problem. So for our first practice problem, we're going to evaluate the definite integral using left Riemann sums for demonstration purposes, even though we prefer to use right Riemann sums. We'll do this once. So by definition, we need to calculate this particular limit. We're going to take it in stages. So first of all, we find delta x. Delta x is b minus a over n. B is 3 and a is -1. So 3 minus -1 over n, which is just 4 over n. Next, let's find f of xi star. But first of all, let's use the left Riemann sum definition. So xi star is going to be given by this. A is -1. We leave I minus 1 as is, and delta x is 4 over n. Now that we have that, we can plug it into the function f of x. F of x is 2 times x plus 2. Let me just write that out, leaving space. So what is x? X is xi star, which we just found is -1 plus I minus 1 times 4 over n. If we distribute in, we'll get -2 plus 2 times 4 is 8. So I'm going to write 8 over n in front, plus 2. Conveniently, I chose the function so that these would cancel, because otherwise, trust me, it would be a very convoluted calculation. So our next step is to find, to simplify, get an expression for this. So we have I equals 1 to n. F of xi star, luckily, simplifies to this. And then we have to multiply it by delta x, so that's 4 over n. So now the important thing to realize here is that if you're summing over I, anything that doesn't have an I in it can be factored out like a constant. So 8 over n and 4 over n become 32 over n squared. And we're left with, that can come out because it's not dependent on I minus 1. And then we use one of the results from before, because we have the difference, the summation of a difference. So we can separate it into the summation of just I from 1 to n, minus 32 over n squared, the summation from 1 from I equals 1 to n. And now let's bring this around here to give us a little more space. So that's going to be 32 over n squared. Now remember that the summation of I from I equals 1 to n was this formula. Okay, and then the sum of 1 is a constant, right? So we know that was n times c, but c is 1, so this is just going to be times n. And we have some canceling that goes on here, so that n cancels with this. And one of these n's cancels with that there. And so, and we can, and also, oh, while we're at it, let's just do the 2 into 32 is 16. So we are left with, this comes out to be, and we're going to distribute as well. So we're going to get that 16 into here. So we have 16n over n plus 16 times 1 is 16 over n. And then we have minus 32 over n. And we see that the n's cancel, and we're left with 16 plus 16 over n minus 32 over n is minus 16 over n, and we are going to take this to the next slide for the next step. So let's call up that expression we just figured out in the slide before. This is our Riemann sum formula. So if we can use this is basically the sum of the area of all the rectangles. So if we had 100, if n was 100, we had 100 rectangles, we would do 16 minus 16 divided by n, which is 0.16. Gosh, that seems like it's getting really close to 16. So to find the actual area, we of course just have to find the limit as n goes to infinity of this expression. And we know that when n goes to infinity, this will go to 0. So the answer comes out to be 16. So let's take a look at this. If I graph the function 2x plus 2 is just a linear equation, and we're looking from -1 to 3. And we can see that we could work out this area. The base is 4, and the height is 8. So the area equals half base times height, half 4 times 8, which comes out to be 16. That checks. Probably wonder why we had to do it using Riemann sums and limits, but it's nice for demonstration purposes. And now we'll get into a practice problem that can't be done geometrically and can only be done using Riemann sums. So for our second practice problem, we are going to evaluate an integral using a right Riemann sum. So here's the integral we'd like to evaluate. And here's the definition in terms of a Riemann sum. So we're going to start by finding the components of the Riemann sum. So delta x is b minus a over n, and b is 3, and a is 0. So that's 3 minus 0 over n, which is just 3 over n. Xi star for a right Riemann sum, it's a plus I delta x, right? A lot simpler. A is 0, as we just established, and delta x is 3 over n. So we could say that's 3i over n more simply. And then now we just have to put 3i over n into f of x. Now, f of x is x squared minus 4x. So whatever you put into f, you're going to square it, and you're going to minus 4 times that amount. And we have 3i over n to put in there, 3i over n. So that becomes 9i squared over n squared minus 12i over n. So now we are going to evaluate the Riemann sum. Not evaluate, but write an expression for it. So we have the sum from I equals 1 to n of f of xi star. So that's 9i squared over n squared minus 12i over n. So that takes care of this. And then we have to multiply it by delta x, which is 3 over n. And right now, I think because the 3 over n doesn't have an I in it, we can actually take that outside. So let's, outside the summation sign. So I'm going to take that 3 over n actually, and I'm going to park it outside here. And then now I have the sum of a difference of two expressions, so I can write that as the difference of sums. So I'm going to separate that parentheses out and write this, 9i squared over n squared, minus, and I mustn't forget that 3 over n, it would kind of have to distribute to both, I equals 1 to n of 12i over n. And now I can actually factor out from each of these summation expressions. So 9 over n squared doesn't have an I in it, and here 12 over n does not have an I in it, so I can take those out. So taking out 9 over n squared, I get 27 over n cubed. And just to use a different color here, that leaves me with the sum of I squared from I equals 1 to n. And now we take out 12 over n, we get 36 over n squared, and that leaves me with just the sum of I from I equals 1 to n. So when we know the formulas to calculate those summations. So that equals 27 over n cubed. And that first summation we know is n times n plus 1 times 2n plus 1 over 6. And then we have to minus 36 over n squared. And that summation of I is n times n plus 1 over 2. We're going to take that onto the next slide so we have more space to complete the calculation. So let's just recall that expression for the Riemann sum, and let's do some simplifying. So we have one of these n's will cancel with one of those to leave n squared, and this will cancel with that. We could do 2 into 36 is 18, and I'm actually going to just do 6 into 27 because it's not a bad decimal, it's 4.5. So that leaves us, let's see, let's collect everything together then. So we have 4.5 outside of, I think I'm also going to FOIL these for simplicity, 2n squared plus 3n plus 1. And don't forget that's all over n squared. And then we have minus 18, n plus 1, and that's over n. And then I'm going to distribute the 4.5 into here. So we get 9n squared plus 13.5n plus 4.5 all over n squared, and here we'll get 18n plus 18 over n, but bear in mind there is a negative in front of there. We'll deal with that right now. So this becomes 9n squared over n squared is 9 plus 13.5 n over n squared is that, and then the 4.5 is just over n squared. And now I have minus 18, the n's cancel, but then I have minus 18 over n. And now if I combine like terms, so I have a 9 and a negative 18 to make negative 9. I have 13.5n minus 18. 13.5 over n minus 18 over n is minus 4.5 over n. And then I just have the 4.5 over n squared remaining. So to evaluate now this definite integral, we'll just take the limit as n goes to infinity of what the Riemann sum we just calculated, 4.5 over n squared. As n goes to infinity, we know that this term is going to go to 0, and this term is going to go to 0, leaving us with an answer of negative 9. So the area under the curve is negative. Now I thought area could only be positive, so what on earth does an area being negative actually mean? Well, let's take a look at the graph of that function and the shaded area in green. So that area in green is really what the definite integral is trying to calculate. And even though area is always positive, so technically that area is 9, when we use Riemann sum calculations, and let's see, and we get let's put a typical rectangle in there, we can see that f of whatever x is, xi star, is going to be negative, in fact, throughout this whole region. And that's why the answer to the definite integral was negative. But bear in mind, area is always positive, but if a function dips below the x-axis and takes on negative values, then the definite integral will be recorded as being the negative value of the area. So we'll conclude this video by just establishing that the definite integral is really net area rather than just loosely being defined as the area under the curve. So let's just clarify what that means. So if I'd like to find the definite integral of f of x from a to b, let's call this a, and let's call this b. And what we discovered is that, well, like if the function is above the x-axis, we know the area is going to be interpreted as positive. If it dips below, as we just saw, so even though, let's call that area A2, even though that's a positive quantity, it's going to interpret that as negative. And let's call this A3. So if we wanted to write so we say we calculated A1 and A2 and A3, how would we combine them to make the the answer to the definite integral? Well, a1 and a3 would be interpreted as positive, and a2, of course, would have a negative assigned. So if you watch my video on area and accumulation, you will see why positive and negative areas make sense in terms of accumulation under a rate function. And of course, you've probably realized that working out definite integrals by using Riemann sums is very tedious. There must be a better way, and there is. And in a few videos from now, when we cover the fundamental theorem of calculus, you will be delighted, I hope, to discover how easy and straightforward it is, and probably be happy to see the back of Riemann sums. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.